Okay, so this is one problem that you need to know. And remember, what we're trying to do is we're trying to approximate the sampling distribution using the normal distribution, the normal model. But there's certain rules or conditions that need to be met in order for the normal model to work, okay? Because if these conditions aren't met, then the normal model does a bad approximation, okay? When the conditions are met, the normal model works well. But if the conditions are not met, the normal model does a bad job. And so I have to teach you these conditions so you know if it's appropriate to use the normal model or not. Three conditions must be met. Okay? And the fact that we can use the normal model to approximate the sampling distribution, that's known as the central limit theorem. Okay? I'm just going to write 3 conditions must be met to use the central limit theorem. Okay? And the central limit theorem is just a fancy way of saying we can use the normal model to approximate our sampling distribution. Theorem. Do I need to spell that nicely? Because that's what we did, right? We wanted to know about the sampling distribution. We wanted to know what's the probability that the next that a random sample has fewer than 50% female. Okay, and to answer that, we had to know the sampling distribution. We used the normal model to give us our answer. But in order for us to use the normal model, okay, or in technical language we call it the central limit theorem. In order to use the central limit theorem, there's 3 conditions that must be met. Okay. The number 1 is our sample must be selected randomly. The items must be selected independent from each other also. Okay? The items or people okay? So we call this the random independent condition. Sample just must be selected randomly, okay? And actually, if it says it was selected randomly, that implies they were selected independent from each other, okay? So selected randomly will also take care of that. But somewhere in your problem, it should say the sample was selected randomly. If somebody says, I picked 50 of my friends, not a random sample. Someone says, I walked around school and talked to people I met. It's not a random sample. We have to do a true random thing, which is like put names in a hat and we draw them out, or use like bingo balls or something, okay? True random sample.
Why wouldn't it be random sample? If you're standing at one point on campus and you stay, and the people that pass you, that would be random, right?
It's not. It won't be random, right? So, for example, at UCLA, most of the students' classes in the arts and humanities are on the north side of campus. And then the people who take science classes are on the south side of campus. So depending on where you choose to stand, the people who walk by you will be different groups of people, right? If you stand in front of a men's restroom, you're probably going to speak to more men than women, okay?
The problem will say randomly.
Yeah, the problem needs to say the sample was selected randomly. Okay? Yeah, arbitrary is not the same as random. Okay? If I just go you, that's arbitrary, but it's not random. To get true random, I would need to get names in a hat and draw them out. Mix them up, draw them out. I can't just.
You have to be blinded.
I'd have to, yeah. Okay. Number 2. Our sample must be big enough. So we have the large sample condition. Okay. There must be at least 10 quote-unquote successes. And at least 10 failures. These are quote successes and failures because those are arbitrary labels. So when we said we picked 25 students and some are going to be female and some are going to be male, we have to label one of those as success and the other as failure, okay? But it doesn't matter which one you label, which gender you label success and failure. Those are arbitrary labels. You just need 10 of one and at least 10 of not that kind. Okay. So if we're talking about orange pieces, we need at least 10 pieces of candy that are orange and at least 10 pieces of candy that are not orange. Okay. If we're not talking, if we don't have the actual counts, then which is the case that we had here, if counts are not provided, then n times p must be bigger than or equal to 10. And n times 1 minus p.
So like if we get a percent more.
Right. So in this case, where we did the random sample of 25 students, n times p and n times 1 minus p must both be bigger than 10. Is that okay?
So you have to test both of those things.
Yes, both must be met.
Okay. And one more?
And there's one more condition. There's 3 conditions, right? The big population condition. Your sample, your population should be at least 10 times bigger than the sample. so let's see if our conditions are met. We'll try an example problem, and you will have some questions on next week's quiz on these conditions. I'm going to describe a scenario to you, and you have to decide if any of the conditions are violated. Okay, so the example was a school is 53% female. Now this is just an example, and we're going to decide if any conditions are violated. Okay, school is 53% female. We take a sample of 25 students, and the school has 430 students total. Okay, are any conditions violated?
Yes. It's not random.
Yeah. Here it just says we take a sample of 25 students. It needs to say we take a random sample. Okay? So it needs to say a random sample. So condition 1 must say a random sample. Okay? Alright, so let's say I change this. Alright? And I write, we take a random sample. Okay, so now this is a new problem. Has the same information as before.
Would we have to test out the number 2?
Oh, okay, yeah. I guess we could check, well, here. So in that case, the first condition was violated, so we know we can't use the central limit there. Now I fixed it so the random sample is met, that random condition is met. What about conditions 2 and 3? Okay, we'll check those, alright? So the random condition, random independent condition, this is met. Is that okay? Because I wrote random sample. Alright, what about the large sample condition? Is that met?
More than 2.
Okay, how do I check that? Alright, so 25 times 0.53 is equal to what? 13.25. Alright, is that bigger than 10? Okay, yes. Bigger than 10. Okay, what about 1 minus p? 25 times 1 minus 0.53 is equal to what? 11.75. This is also bigger than 10. Okay. So both of my numbers are bigger than 10, so the large sample condition is met. Okay, so I'm just checking n times p and n times 1 minus p. And I want to make sure both of those numbers are bigger than 10. Okay? No? Yes?
Yep.
Alright, and the third condition, what's my third condition? Big population condition. Alright, is that condition met? So my population needs to be at least 10 times bigger than my sample. So how big is my sample?
25
25. What's 10 times bigger than my sample? 250. Is my population bigger than 250?
Yes.
And then
What's 10 times?
250. 10 times 25.
Yeah.
Okay. My population is how big? 430 students. So the answer is yes. There are 430 students. Okay, so the big population condition is met. Okay, so all three conditions are met. Okay? Alright, how's that?
Yeah.
Okay. Another example? No?
Yeah.
Yeah, okay. Can I erase this?
Yeah, but you do it slower.
Do it slower?
Yeah. Yeah.
I did it too fast?
Yeah.
You wrote like the question and then asked two.
Okay, I
Like I didn't
apologize.
have time to finish writing the problem.
Alright, I will work on that. Alright. Then I will write a question and okay. So we take we want to study, I don't know, we want to know the proportion of people with people with, I don't know, tattoos. Okay? So we take a random sample of 30 people. 23 of them do not have tattoos. I don't know. I'm just making up numbers here. The population is all U.S. adults. Okay. Go ahead and see if any of the conditions are violated. So there are just three conditions you need to check. You should list them off. Is it met, or not met? we doing? Good? Bad? Seven. Need another minute, or are we okay? One more minute. Check your math there. All right, yeah, that's a minute. Okay, is the random and independent condition met? Yes or no?
Yes.
Yes, this is met. How do we know? It says we took a random sample, so that's good. Okay. Large sample condition, is that met? Yes or no?
No.
No. Okay. How do we know it's not met? Okay. Do not do 23 times 0.3. Where are we getting 0.3? 30. Okay. All right. So what's my n? My n is 30, and what's my p? No p was given. There's no p, okay? So don't do any multiplication here. Don't do 23 times 30, okay? Yeah, and don't do 23 times 0.3. Don't turn 30 into 0.3, okay? That's like, you're just like, I see students do this all the time. They just think, oh, here's a number. I can just move the decimal around, okay? You can't do that. You can't do that. Okay. In this case, we want to make sure there's at least 10 successes and 10 failures. Alright?
Wait.
Can't know that the condition isn't met?
No. I'm going to say we want 10 successes and 10 failures. Yes, we have a question.
No, I was just going to say there isn't 10 successes and 10 failures because there's not 30, there's not 10 people with tests.
Exactly. Alright? So whatever we label successes and failures, okay? We have people with tattoos and people with no tattoos.
And there's only 7 with the
Yes.
Okay, so how many people have no tattoos? 23. How many people have tattoos? 7, right? Can we see that? Okay, 30 people total. 23 don't have tattoos. 7 people do have tattoos. Okay? Both of these numbers have to be bigger than 10. This is bigger than 10. This is not bigger than 10. So this condition is violated. Alright?
Yeah.
So in this case I didn't give you a proportion, so you don't need to do n times p and n times 1 minus p. Here you're just looking for 10 successes and 10 failures. Okay? Alright? Huh? Yeah, this is why we do it in class, so you learn, right? Okay. Big population. Is that meant?
Yeah.
Yeah, okay. So my population needs to be at least what? Should be at least 30 times 10, right? My sample is 10 people, so it should be at least 300 people. And what's my population? US adults, okay? So, are there more than 300 US adults? Yes. Okay? Yes.
If you were to do 23 divided by 30, and that's like 76%, that's 76% of people don't have tattoos, right? But that has like nothing to do with like the equation or whatever, but that's the percentage for people without tattoos, right?
Repeat this question again.
Okay, so you know how there's like 23 divided by 30 and people with no tattoos?
Yes. Yeah, I mean, you could force to get a p hat calculation, right? You could say p is equal to 23 divided by 30, and you get something like 0.77, okay? And then you would do n times p, right? You would do 30 times 0.77, and what does that give you? It gives you 23. All right, so you're back to square one, okay? And then you could do 30 times 1 minus 0.77. And what's that going to give you? That's going to give you 7, okay? So yeah, you would get 23 and 7, and you would compare those to 10, and then you would get the same thing here, okay? I mean, this is completely valid, and if you're comfortable with that, that's fine. It's just kind of an extra step, though. Okay? But no problem, no problem. This is not wrong. It's just extra steps, okay? As long as you do this correctly, you'll be fine, okay? All right, is that okay? So next week on the quiz, I'm giving you all the everything you need to know. Everybody should get 100% on this quiz, right? You're going to see a few questions, maybe like 3 or 4 of them, and it's just going to be like this. I'm going to just have a situation described like this, and you say, are any conditions violated, okay? And you just have to say, this condition is violated, or no conditions are violated, okay? Alright, and the last thing we got to learn today, and you will see a question on this quiz next week, is making confidence intervals. Alright, the idea behind a confidence interval is that you've taken, here, I'll let you guys write confidence intervals, and then let me explain. There's only 2 words to write. Huh? Okay, confidence intervals. Pay attention. The idea behind a confidence interval is that we don't know the proportion that exists in the population. We don't know the population proportion. Okay? So remember, earlier on when we were talking about the Reese's Pieces, I said I obsessively picked out all the candies so I know exactly 30% of the candies are orange. Okay? But in real life, we're generally not that obsessive about our candies, okay? And so we don't know exactly what exists in the population. So now I said, you know, I still like, whatever, we're dealing with Reese's Pieces. I just buy bags from the store, I cut them open and I dump them into this bucket, okay? I have no idea exactly what proportion is orange. And there's like thousands of them, I don't want to count them all out, okay? So if I just take a scoop of candies, I mix it up so it's random, and I take out a scoop of randomly selected candies and I dump them out, and I count that 35% of the candies are orange in my sample. So let's say my sample has 200 pieces, and we find that 35% are orange. What does that say about the bucket?
Nothing.
It tells us nothing? Huh? So let's say there's 30,000 pieces of candy here. It's a giant bucket, all right? And I picked out 200. It's a random sample, and in my sample, 35% are orange. Does this tell me anything about what's in the bucket?
35%.
Okay, there's some orange candies, okay? It's probably, yeah. Not more majority, only 35% is orange in my, okay? So, well, if you had to just place wagers, right? Somebody said, okay, let's bet some money. How much percentage, we're going to hire someone and they're going to count out all the orange pieces, okay? Or I've got this robot. He's going to do it. He's going to do it. So what would you guess to be the proportion? That's Huh? 35. What?
35.
29%, huh?
35
What's not
is the
orange?
same
What
as
would
the
you guess is
population.
not orange?
No, it is orange. What proportion of this giant bucket is orange?
35.
Okay, if I just took a sample of 200, right? In my sample, 35% of my sample was orange. This right now serves as my best guess for what's in the bucket, okay? I have no idea if this sample is truly representative. It may have more orange pieces, it may have fewer, but my sample had 35% orange. So my best guess right now for the bucket is 35% orange. Okay? Now, if the bucket turns out to be 33% orange, would we be shocked?
No.
No, we'd be like, oh, okay, that seems reasonable. If the bucket turned out to be 37% orange, would that be shocking? No. Okay. If the bucket turned out to be 80% orange, would that be shocking? Yes. Okay. All right. So let's play with our intuition here. Okay. 200 candies, 35% of my 200 were orange. If the bucket turned out to be 30% orange, would that be surprising? No. 28%?
No.
25% orange? No? Yeah. Would you be surprised? Right?
How do you mean?
Huh? Maybe.
How do you mean?
So the sample of 200 was 35% orange. It's a random sample, but my sample was 35% orange. Would we be surprised if the robot counted all the orange pieces and said the proportion is 22% orange?
I will be that shocked.
Yeah, it would be
All
that.
right. Well, some of you said I might be shocked. Some of you said, I've seen her doll. Takes a lot to surprise me now. All right. Well, let's talk about this. Okay. A confidence interval. A confidence interval says, okay, I've seen a sample, and I'm going to give myself some wiggle room here. Okay. So I saw that my sample was 35% orange, and the confidence interval allows us to calculate what we call a margin of error. And it says, plus or minus, give or take 5%, or give or take 7%, okay? It depends on what the formula spits out. There's a formula we use. And the confidence interval will say, oh, you know what, 35% with a margin of error of 3%, okay? Sometimes you see that during election season, right? It says candidate ABC is winning, 54% to 46% with a 2% margin of error. You guys know what I'm talking about or not?
Yes.
Okay, yes. So that just means, so he says like 56% with a 2% margin of error. That means his actual percentage is somewhere between what? Probably between 54 and 58%. Okay, because if it's 56 with a 2% margin of error, you subtract 2 and you add 2, you get 54 to 58%. Okay, we do the confidence interval is basically the same type of thing. We use our sample proportion as our best guess, and we say plus or minus a margin of error. Okay, and there's a formula to figure out that margin of error. So,
Write down what you just said.
yes, I will write everything down. Okay, not everything, but everything, yes. Okay, so confidence interval. The idea is, alright, so here's the big idea. We do not know the population proportion P. And we can't afford to figure out the true value of P right now. Maybe someday in the future we will. But right now, we don't have P. But we observe a sample. Okay? Of size n. the sample proportion is p hat. So we're going to create a range of what we consider plausible or reasonable values of p. This range is our confidence interval. Confidence interval. Yeah, sorry. It's messy there. It's less messy up there. Okay, but it's the same word. Okay, so our confidence interval and I'm just going to shorten confidence interval to CI. Okay, for CI, we will use p hat as our best guess for p. So I've got a giant bucket, 30,000 Reese's Pieces candies. They're all mixed up, shuffled well, or stirred up well, I don't know. And I've taken a sample of 200. In my sample, 35% are orange. I don't even like Reese's Pieces candies, but here we go. 30,000 pieces in the bucket. Okay. Sample of 200 candies. 70 of those are orange. So p hat is equal to 70 divided by 200, 0.35. What can we say about p? That's the example we're dealing with. So right now, okay. No, that's good. Check on the Clippers game. You guys want to know, or is someone recording this? It's there's 8.5 minutes left in the fourth quarter. Clippers are up by 2. Nobody knows what's gonna happen, alright? That's way too much time for something crazy to happen. Okay. The Clippers are a basketball team in Los Angeles. If you aren't aware. There is a championship tournament going on right now. And they are playing Oklahoma City. Alright, for our confidence interval, we use p hat as our best guess for p, okay? So 35% will go in our confidence interval, okay? So our confidence interval, our CI, will look like this. Okay, it's going to be p hat plus or minus a margin of error. So it's going to be 35% plus or minus the margin of error. Okay? The margin of error is calculated by using a formula, okay? So we have to pick a confidence level to correctly determine our margin of error. Alright, is this okay? So if my margin of error ends up being 4%, then I would say I feel like P should be between 31 and 39%. Okay?
Right.
That's what we'd say.
Wait, I have a question.
Yes.
If you, okay, for confidence intervals, do the 3 previous rules apply? So when you say a random sample?
Oh, yeah, they do, and I should say random sampling. Thank you.
Okay, just checking.
Okay, the same, because this is all based off of the central limit.
Yeah, I know you said out loud, but I was
Yeah.
just checking. So the same rules still apply?
The same rules still apply. Alright, so the margin of error is equal to z times what I call what's known as the standard error, and that's p hat times 1 minus p hat divided by n. This should look familiar, except we put hats over the p's. Alright? And they're hats because we don't have the actual p. If we had the actual p, we'd use that. But we don't have it.
Is it C squared times?
Yeah,
or what
z
is that?
times. How do I indicate times? A dot. Yeah, it's a special. Maybe I'll put a z star. Okay, it's a special z. It's a special z score. Okay, and the z's depend on your level of confidence. Okay, so remember we're creating a range for where we think the true value of p should be. Okay, now I could say the true value of p should be very close to 35. Maybe it should be between 34.5% to 35.5%. That's a very narrow range, okay? And somebody says, how confident are you about that? I'd say, I'm actually not very confident, okay? Then I could say, well, okay, let's be a little bit more generous. We'll say a margin of error of 4%. So then I say the p should be between 31 and 39%. And somebody says, how confident are you? I'd say, I'm pretty confident, okay? And somebody says, I want you to be 100% confident about where P is. What would I have to say? You want me to be 100% confident about where P is going to be? Okay, well then I'm 100% confident that P is between what? Between 0 and 100%, okay? And I'm 100% confident that the proportion of orange candies is between 0 and 100%. And they go, that's not what I was asking for, okay? So if you want to be more confident, you can make your range wider so you're more confident that the P is in there, okay? But if you make it too wide, it's useless. So you can pick the confidence level, okay? And so common values for confidence. Where did oh no, we don't need to Alright, common values for confidence, and these you're going to just have to either memorize or make sure you write down on your note card, okay? Memorize or write on your notes. Alright? You come next week for the quiz without a note card and you say, I forgot. I'm going to say, well, I told you. You need to know these numbers. Alright. So there's levels of confidence. We got 80%, 90%, 95%, and we'll say 99%. Okay? For the different levels that we're going to use, for 80%, Z is equal to 1.28. For 90%, Z star is 1.645. Okay? Well, as long as you know when you see the Z, it's talking about this Z. Okay? 95% is 1.96. And for 99%, 2.58, I believe. Yes.
Who figured that out? Where does that come from?
It comes from our normal model table, but not too worried. All right. So those are the 4 numbers you need to know. Okay. So when you put everything together, all right. So make sure you put that on your note card. Don't come crying to me next week saying you didn't put it on your note card and you forgot. Okay, so when we put it all together, our confidence interval looks like this. P hat plus or minus Z star times the square root of P hat 1 minus P hat over N. Did they teach you Z is Z or Z or Z? Z. For our international students. This is America, we say Z. Huh? No, we say Z. In Britain they say Z. Huh? Z. It's like X, Y, Z. I don't, do they sing the alphabet song the same? Do they teach you is there an alphabet song?
We sing it in Swedish.
Huh?
We sing it in Swedish.
The
alphabet
for
song?
the alphabet
you
song?
mean, yeah.
Is it the same as Twinkle Twinkle Little Star?
Yeah.
Yeah, okay. Okay, that's good. Someone told me for Hebrew it's Yankee Doodle. Is that right? No? What's the alphabet song?
It's its own song.
It's its own song. Okay. Someone told me. Alright. They were wrong. Thank you. Alright. Alright, so let's make a 90% confidence interval and a 95% confidence interval for the proportion of orange pieces in the bucket. Alright, you should be able to do this. I haven't done an example, but you should be able to do this. It's just putting numbers into the formula. Okay, just start off with the 90% confidence interval.
we have to look something up in the equation?
No?
Literally just put in that number?
Yes. N is 200. N is your sample size. Third or fourth decimal, it's up to you. You got it? Great. Good. Good.
So you have to use this one, right? As a key? Yeah, because it's so.
Yeah, read you. All right. Question. Where did I get the? Oh, I'll get to that. I will explain. N is 200. That's my sample size. N is always my sample size. No, that's how many orange pieces. That's not my sample size. Question back there? Okay. Yeah, 70 is not in this formula.
When you say that n should be the number, n should be the number.
N is always going to be our sample size.
In these things, but all things we already said that n was how many.
Yeah.
Right?
How many in our sample?
Yeah. So now it's a sample. Oh yeah. So
Yeah, it was how many in our sample. How big our sample was. So it's still our sample size. Okay. All right. Okay. Let's go over this. Okay. So we have n is equal to 200. This is our sample size. All right. Don't mess this up. This will mess up everything else. P hat we determined was 70 over 200 or 0.35. P hat is 0.35. And what is the Z star I'm using for 90% confidence interval? 1.645. Great. So I just come over here and I just plug in all the numbers I have. I do 0.35 plus or minus Z star 1.645 times the square root of 0.35, 1 minus 0.35 divided by 200. Okay? And so it's a good check on your calculator. Make sure if you do 0.35 times 1 minus 0.35 divided by 200, take the square root of that and multiply that by 1.645, you get 0.055. It's like 0.05548. You didn't get that? Okay. Okay, did you get this to be 0.03373? Do we have that? No? Okay. So you have to figure out how to properly use your calculator. Okay? And then when you multiply that by 1.645, it becomes 0.05548. Okay? And I rounded that off to 0.055. Yes?
Is there a way to get the range?
Hang on, let me take your question. Alright, shh. I'm sorry.
My calculator when I solve this and it gives the answer because I found the answer, but if I don't have this one,
I don't. Your calculator doesn't have a plus or minus button. So what are you?
I just plug everything in.
Okay.
Like I do the plus or
Minus. Okay. Okay. That's fine. All right. I would say just do this part and then do plus or minus that. Okay. You'll save yourself a step.
Right? Like just do the from the C star all
Yeah.
first,
Do this part and you
then-
get 0.055.
Yeah.
And then do 0.35 plus that, and then 0.35 minus that.
Thank you.
All right, is everybody okay?
No.
Quiet. All right, so this is the low end of my interval, and this is the high end of my interval. All right. So now this is my range of plausible values for what? Yeah, but it's okay. This is my 90% confidence interval for what? P. And what is P? The proportion of orange candies where? In the bucket. In the population. Okay? It's not a confidence interval for the proportion in my sample. It's not a confidence interval for future samples. It's a confidence interval for the proportion in the population, which is my bucket. Yes?
I'm just asking, so we don't do anything with the 70, you just have to use it to get
The 70 went into the calculation of 35%.
But then you don't need it for the rest.
You don't need it for the rest.
Can you write down what we said that this was?
Yeah, I'll write that here, okay? This is a confidence interval for P. The proportion okay? Not for the proportion in the sample.
No, because you already know that.
Yeah, exactly, exactly.
That is 0.35.
That is 0.35. That's right. All right. One more thing I'm gonna write on the board, okay, and then we'll try one more example, and then I'll let you guys go home. Yes.
So the p hat would also be like the n, right? Like the 200. Or
So this is we would call this, I guess, x over n to get my p hat. All right. So the interpretation, the final interpretation of this and this is this part that students, maybe they struggle the most with, I don't know. Okay. Okay. You say, we are 90% confident. Right? So our sample was 35%. And I said, okay, we're going to give ourselves some breathing room, 5.5%. So that gives me a range between 29.5 to 40.5%. Someone says, how confident are you that P is in there? Between 29.5 and 40.5. I say I'm pretty confident. In fact, I'm 90% confident. We are 90% confident that P, and what does P represent? The proportion,
Of the population.
yeah, proportion of orange candies in the population. Is between what? Is between 0.295 and 0.405. Someone says, do you think you have evidence that it's different from 28% orange? So our sample was 35% orange, 200 candies. Someone says, do you think, does that make you feel pretty confident that it's not 28% orange?
Yeah.
Yeah, because why? 28% is not in between these two numbers, right? So, do we have evidence that the proportion is not 28%?
I mean, there's a possibility that it's really low.
Wait, hang on. So, that the proportion is not 28%? We say yes. 28% is not between our interval, or not within the interval. Or between 0.295 0.405. But is it possible that the proportion of orange candies is 28%? Yeah, it is possible, but we would say that's surprising. Okay? So some of you might not be surprised, but according to our confidence interval, if we take, even if there's 30,000 pieces of candy in this bucket, if we mixed it up and I took a random sample of 200 and I found that 35% of my sample is orange, I would then be surprised if the robot counted all the candies and found only 28% of them are orange. Okay? We would not be surprised if the proportion orange was in between these two numbers. Okay? But if it's outside of that range, we would be surprised. Okay? Is that okay?
Yeah.
Alright? Okay, so you'll see some confidence interval questions on next week's quiz. And that will be it. Okay, we'll see you guys in a week.